Jannis asked me, and also Christian Deppe, to talk about theory that matters. That means now that I will not talk so much about the quantum stuff that you all do. I followed yesterday most of the talks, and I find it quite interesting to see at which stage we are, and remember me about other topics that we did. And my idea is now to talk about something, how you really can make theory work. Right now, we heard a lot of talks about this could work and this, but in the end, whether it's successful or not, it's not decided on paper, right? It's decided out there in the real world. And sometimes we have these two worlds of theory and implementations, and some people believe only in one or the other. This talk is really a motivation, and I'm advocating to have a peaceful life with both of them and how to interplay both of them to get the best results out of that. In order to explain that, how we do it, I can only do it by an example. I will just shortly introduce what we are doing here at the chair, and then maybe you will understand how this matters for the theory that matters. So first of all, what we had done here when we started the chair, we had a lot of flagship projects, right? We are known, for example, for something that is 5G, the communication part, where you think about low latency communication, security-wise, what you can improve there. And with this topic, we also had a new way of looking into information theory, which kind of novelty we would like to plug into the networks, because with 5G, suddenly everything was softwareized. They opened the door for innovation. And with that, we had several other projects coming in. I will only name a few. For example, our excellence cluster, CETI, Center for Tactile Internet, where you then really would like to exchange skills and skill sets over the internet. You can even not only transport audio and video, also haptic information, something like social touch that you would like to have over the internet, something that is very nice in the times of COVID, right? So then there are other things like 5G campus, where we build our own 5G networks nowadays. We are bringing them out to different locations. We also go to clinics and so on. And if you ask people, what is the chair doing? And then they will tell you, yeah, there are some topics, some use cases, energy, automotive, industry 4.0, medicine. Some other will tell they're talking about different things like virtualization platforms, communication architectures, or information theory. They know us from that perspective, but most people will maybe say, oh, I've seen the demonstrators, right? A lot of people think we do a lot of demonstrators, or we implement a lot of stuff. When I was postdoc and then later also associate professor and other stuff, I remember that while I was not in Germany, and we implemented stuff on mobile phones. And then the real professors in Germany said, this is not real research, right? If you do something on mobile phones, that must be some games or something like this. I come back to that. Now we are not on phones anymore. The things become a little bit bigger, right? This is, for example, it's the 5G campus project, where you have a standalone 5G network inside the box, together with a demonstrator. Here, for example, a demonstrator how to teach a robot how to make cocktails by a human teacher, right? And this in minutes. We also have these bigger trucks that can go around demonstrating our research to the public. And then we have dedicated demonstrations, for example, the CEO of Volkswagen here, where we explain them how to teach a robot with intelligent clothing. Or, for example, in the clinic, where we have robotics to operate stuff. And sometimes if we cannot show it in the real world because it's too big, sometimes we also use some kind of unity models or virtual models, where we have an emulated, half emulated, simulated world, right? So what does this have to do with theory that matters, right? It is something that we developed over the time, especially when we were in Aalborg, or I was in Aalborg with my group, and we thought about how can we really interplay theory and also implementations, right? And most people know that there's a theory and you implement it, right? And this is applied science, and then that was not what we really were interested in. So to show that theory works, is sometimes nice, and we also did this not so often, but what for us is more important is the way back. So once you implemented it, normally if you're really on the edge research, you do it, you fail. And if you understand, I mean, we are researchers, we understand that failure is an option and failure is the source of new ideas, right? And in this circle between theory and implementation, we came up with a little bit more complicated picture, and this was our picture for theory that matters. So what you see here is on the top, the fundamental research, your theory, concept, mathematical analysis, modeling for a certain topic. I just called this generally here the research areas. These are the orange parts here. So these parts is what your research is, and you can cluster it in a way how you would like to do it. And there's the lower bottom with algorithm, protocols, parameterization. When it's protocols, it's more my world because I come from communication networks, of course. And then you would like to implement this, right? And there are different ways. The easiest way maybe is a simulation. But whoever is doing a simulation also knows that whatever you will, let's say, tweak everything until it works for you. It's just a model of what you have in your head anyway. And I would be surprised if your simulation is not working. Most people don't have a problem to show that their results work in a simulation. If you have real software in the loop, so for example, if you have a TCP stack that you plug into that and it behaves like a real protocol stack, it's already more convincing, right? But even more convincing is if you plug in maybe some hardware elements, right? Some real hardware elements that are already available on the market. If you think about quantum now, there's not so much available, right? We came from a different world in communication networks. There were so much things that we could plug in. In the new world, the communication networks, there's maybe little that we can plug in there. And in the end, it's not only hardware that we have in the loop, we build a whole test bed. So what you saw before, that are real test beds, right? And when you have the two things like theory and implementation, so theory on the upper part and implementation on the lower part, then you have on the right a little bit what I call exploitation, right? How to write papers. I think everybody of you knows how to do that. Making patents maybe also, but what is about building the demonstrators? How to bring this also into teaching? How can you break down a bigger test bed for teaching things? Can you take part of your software and make it open source, right? Or can you have a tech transfer? So later I will talk about startups. Can you plug something out of it and say, hey, why not making a startup out of that? And I think in order to show you how this works, I brought you one example for that, right? Otherwise, it's hard to explain how it works. So if you look at this research area, I have to fill it with something. And before I do this, let me just say what we do with, for example, simulation. Here's a very easy wireless mesh, cellular controlled cooperation scheme that it looks often like this in our world. Real test beds. You have seen some in the first way, but here you see, for example, for the Center of Tactile Internet, where we have a humanoid that has also a human that is interacting with a humanoid robot that we built. And there we explain people latency. Also on the top, you see some very easy test beds explaining humans what latency is, or down there, some cars that can go fully automated over an intersection, right? So these are then the test beds I'm talking about. And in order to explain you our concept of theory that matters, let's go back to one research topic that I was interested in. I was interested in that because I worked on something totally different, on cooperative wireless networks. And if you work on cooperative wireless networks, you will come to the point where you can think about source coding that to make it intelligent, that people can cooperate. But in the end, you want something more general. And at that time, I had contact with Ralf Kötter at Munich already, and we discussed about network coding, where I was still a fan of source coding. He introduced me to network coding, and network coding at the time was a special form that I was really interested in because of the agility of the cooperative clusters in wireless communication. It was random linear network coding. So if you know what a code is, you have these packets on the right side, P1 to P6, and you want to get out the coded packet C1 to C6, and then you have a coding matrix. And normally, if you want to become famous as a professor, you give this coding matrix your name and you find out special elements you put in there. The nice thing about random linear network coding was that you randomize this matrix. And I was new to the field of the whole random linear network coding. Even network coding was new to me. So I was really blind and blunt to say, okay, let's start that and let's just implement that. And there were already some voices telling us, random is never a good code. It is too complicated. It will never be running on an embedded system. And later when we talked to Gallagher, Gallagher said, oh, I did my PhD on LDPC, and now they are trying to implement it in 5G, right? So this is the lifespan of a professor when you have something new, right? So there was also the assumption from Gallagher and others that you need also several decades to make random linear network codes really suitable for embedded systems. And maybe this whole idea of a random code, why should a random code be good, right? And the theory was at that time already so strong to say, if you have random linear network codes, from the network perspective, you can always get the min-cut max flow out of a network, which is something for communication network people, right? Talking about the complexity, you have to deal with Gaussian elimination, and then they will say, hey, the complexity should be cubic, be careful, it cannot be done. What was really nice about the network codes that they came handy with is that instead of this form, if you build it up like this, if you have a number of packets like G packets, you can create with your randomized coding coefficients even as many coding packets as you want. So it's a rateless code. That at the time was something that fountain codes did for us. And it was the only good thing in coding for the last decade was that we had fountain codes. It was good for streaming, right? But network coding gave you that for free. And on top of that, it had also good featured when you talk about multi-hop networks, multi-pass networks. And yesterday, there was a nice talk about multi-hop with quantum communication. I liked it very much because there's a lot of these questions that we also had in the codes. And you can really intervene these two topics very nicely. So when you do that, you come back to the picture. Now I erased everything on the top. I just say, okay, let me think about network coding. And the first thing I want to talk about is resilience. So you always take a code when there are errors, right? When there are no errors, you don't need a code. And most people thought maybe RQ would be a better thing. Why you use a FEC code here? And later I will show you what the superiorness of the network code is about RQ maybe. And then there are different things you can think about resilience, network topologies. But the one thing that was also interesting is field sizes. So let me go back. When you have your randomized elements here, and you don't just choose 0 and 1s here, you can have random numbers, and of course they are not random or floating points because that is not feasible on an embedded system later on. You're operating on some finite fields. And the field size was very interesting for the performance of the codes. The notion that a random code is bad comes from early papers where they only had 0s and 1s. So now when you have a higher field size, then you can find out it's interesting that you have nearly an optimal code, right? So let's look only at the field size. And then you say, okay, if I want to implement that, I can then build by a simulation that works nice. Then I can do software in the loop. Everything is fine. And then I put it on a mobile phone. And if I do that, then I find out which kind of field size should I do. Here you see an analysis from the simulation that you say, okay, the blue one is the performance curve of a binary, then 2 to the 2 and 2 to the 8. And it tells you when of a generation size of 50 packets, when can I decode? And it seems that if you have a binary field, also a low field, you need a lot of packets to receive until you can decode. So the assumption was okay to say, maybe the binary code is not so good, but higher fields were good. So all the theory guys that in the paper had 2 to the 16, 2 to the 32, and so whatsoever. When we implemented that, in this hardware in the loop on the phone, we found out suddenly it did not work. Actually, it worked, but it was not usable. So this is a result from 2007. I think it was the first time somebody we got network coding on an embedded system. Maybe somebody find a prior work. I would be surprised, but I was just going to say it was our first work. And we did some tweaks. We really made it nice to make it easy for the phone. We had pre-allocated memory. We generated the random numbers beforehand. All of that were done. And then we looked at the highest throughput we can get. And this is throughput in kilobytes per second over the number of packets we want to code together. And of course, if you remember the cubic formula in the beginning, the more packets you want to code together, the throughput, the coding throughput drops dramatically, right? But even if you have a very small number of packets to code, you get only 80 kilobytes per second. And at that time, the Nokia phones, they could have, for our cooperative wireless networks, they could send with 5 megabit per second from device to device. So the coding was slower than the actual transmission. So that is not working, right? So then you go, then you look at this, and to make the hardware in the loop work, you have an optimization criteria. So you go back to the algorithm protocols and parameterization and say, what can I do here on the implementation side? And when you know these Nokia phones, they had, for example, a 3D chipset for gaming in there, and we misused it for calculation of our coding matrices. With that, we tweaked it a little bit, we got it a little bit better, but you never come to the testbed with that. Because when you want to go to the testbed, it has to run on all the phones, maybe, right? On multiplicity of phones. Otherwise, it's not very convincing. So you can tweak it a little bit on the one special platform, but not for everything. And that is where it really becomes interesting. And that's the nice thing where we always say, we go back to the whiteboard, right? So instead of fiddling around, trying new platforms or waiting for hardware acceleration things, we just ask ourselves, is that what we did in theory the right thing? And I remember sitting with Ralf Kötter in a beer garden with a lot of beers and saying, what can we do to make this thing work on an embedded system? And then there was several things. For example, wait a minute, these binary fields, they are fast, right? So when they are fast, how bad are they? And at that time, nobody knew it really. Actually, you just have, if you have a generation of G packets, after a while you find out you only have to send 1.6 packet more. If your generation is very large, this 1.6 is not a problem. So maybe a new field size is the real solution for that. But then we found also out, if you look at the coding matrix, it's very complex because there are so many unknowns. It's like playing Sudoku. The more things you know, the better it becomes. And there are sparse coding matrices. So adding zeros, I will show you what I mean by that, has some good ideas. So let's take this coding matrix and you just fill in zeros here, right? Or you fill in more zeros into that. The more zeros you put into that, the less complex was it for the embedded system to calculate. But you also increase the risk of not being able to decode the matrix in the end. And then we played around with certain ideas of making this density of sparsity tunable, right? And because we found out in the beginning, it's never a problem to be sparse, but towards the end of the generation, it is. So maybe we just go up with the density. This is called tunable, for example. So there was something in that where we said, okay, now we can play with the complexity, and suddenly it worked, right? And here I make everything green to tell you we can do it now even for the test, but we had a lot of nice demonstrators with that. We built our own software library with that. Also a startup is now selling this kind of coding library. And it was 2013, so 6 years after we found out that we have a problem with complexity, that we presented our results. The library we used was called Codo. and there are two of them. One is here multi-threaded, and the other one was not multi-threaded, whatever, with the sparsity level. And we compared it to different other libraries at the moment. And I only want to name two, gRazor 2.0. That was a very good implementation from people from Austin, Texas, I think. They only did Reed-Solomon. So not network code, but Reed-Solomon. They were quite good in using the hardware acceleration, and we learned a lot from them. And the EACN, that was an implementation by Intel. And what you see then here by the results is that we even beat the Intel guys. They have hundreds of engineers with their Reed-Solomon implementation on an Intel chip with the coding library that we presented here, right? With a lot of tricks, and I will not go into detail. But that was the moment when we had the tipping point. Now, there's even more in that because of the implementation. What we found out, it's very hard to parallelize Reed-Solomon, right? But it's very easy to parallelize, not easy, but I would say there are some tricks to parallelize network coding in a higher degree than Reed-Solomon. And with that, there was an interesting finding. So we had students that could not multi-thread, but really use a multi-core platform. And if you take a simple Raspberry Pi, then with 4 cores, they got a speed up of 10. So now you will say, how can you have, from theory, when you have 4 servers instead of 1, why can the speed up be 10? And that has to do with the architecture of the embedded system. What is the chunk size of caches? Level 1, 2, and 3. What can you do in order to maximize the packages in these caches? There's nothing in theory that you ever will have a look at this, but this you get from the implementation. And you feed back this to the theory, and the theory guys have new degrees of freedom to come up with new ideas. If you tell them, hey, we have complexity under control, come up with the weird stuff, right? But there was more, right? Once we implement this in the way we are doing it currently, then we got on the Raspberry Pi, even 2013, these were the coding speed now that we achieved for different field sizes, right? You see there also to the 16, even 2 to the 32, right? -5, there's an optimal prime field. And if you look now at the throughput, if you remember on the phone, we had something like kilobyte per second. Here we have megabyte per second. And you see, okay, binary fields are super fast, right? Optimal prime fields are not following the trend that larger fields are worse. There is some findings that sometimes the optimal prime fields are as good as the binary fields. But what was more interesting, if we double the generation size, we only halve the throughput. So this is not cubic in complexity, right? And we thought about this. Why is this not cubic? And the reason for that is because we are not in the right range. So the complexity of our solution becomes cubic when you go for generation size around 1000. But normally nobody is using this big size of generations at the moment, right? So something between 8 and 32 is what I have seen in current implementation of network coding. So also a finding that was quite interesting and also spawned some research in this area of complexity. The other thing is, you know, when you would like to improve the performance of your coder, you ask yourself, where do you lose the time actually? Is it the calculation actually? And here you see a plot, time consumed totally when you have a generation size of 256, so quite big, just to show you the impact. And then how big is your packet, right? 1,500 is an MTU size of an IP packet, for example. And then you see the green one is the actual math coding, and the blue one is the time you need to create the random numbers. So if you have a shared randomness and you don't pay for it, that would be good for network coding. I leave it up to your imagination what I want from you now, right? And this impact becomes even worse if your packets are not big. If your packets are very small, the time for the generator, for the random number generator, is way bigger than the time we need for calculation. And you say, okay, this packet size, what is this? This is the actual size you need in Industry 4.0 to talk with a KUKA robot, right? So creating random numbers is something that I would like to have handy for my coder, for example. So that was just something we did about resilience, but you can do more about it. For example, latency, right? Then again, you start again. I just want to do it very quickly. We found out that the sparsity is good for complexity, but we shoot sparsity randomly into that, right? But then we find out, why don't we order it, right? Why don't we just say, if we, in the beginning, our density is big, so you see here the blue ones, they represent non-zero coefficients, where the white ones are zero coefficients, and we called it on the fly. And suddenly we ordered them in the beginning just to reduce the encoding vector, because when you have them randomly, the zeros in that, your encoding vector is large. But when you say there's a certain density and you just have an index where the zeros will start, then you can even optimize for the encoding vector. It's a specialty of network coding, right? But when you did this, we suddenly found out that you got also instantaneously decodable packets, which is good for low latency communication. Robots like that, right? So what does it mean? Here you see the encoder that is creating this triangle that I showed you before, and you see what happens when you have a normal picture. Right, in the middle is the picture, on the right is what the decoder is doing with the packets that come from the encoder, right? So I do this now with different fields. The first one was binary, and now we have 2 to the 2. And how can you see what kind of field size I'm using? When you look at the color, some of them are black, now some of them are even gray. So the field size is represented by the grayness factor. So and then you see the picture is not coming in the end, like you would get it in the block code. You get it, so to speak, on the fly. And when you do this, then suddenly you find out, why do I have to, if I have some feedback what the other side get, I can even clean up my triangle on the lower side, and that reduce the complexity again, right? And maybe you have the right amount of packets that are encoded over a sliding window to have both resilience and low latency, right? Okay, and this back and forward between theory and implementation over the last years gave us some very good results, some nice papers and whatever, some startups, and I only can motivate this. Here, again, the sliding window, just that you saw it, now you see that we have the encoder is making something like a tunnel, right? Sending something over to the decoder, and in the middle of the picture, I think you would not be able to distinguish whether it's on the fly or whether it's sliding window. You only see it in the encoder, right? Good. So coming back to this theory that matters, after the latency, you can even think about heterogeneity. Can I have codes where nodes are coding with different field sizes? That is also something was interesting. There's telescopic codes, fulcrum codes, all a result of first the theory, but then also the implementation to prove that this is doable. And these kinds of heterogeneous codes are very nice, because a network code is something that happens in the network. At every node in the network, something could happen. Despite the other codes that only are end-to-end, right? Then you only agree sender receiver. Can we agree on a code? Thank you very much. If you do it over the whole network, you will always find out we have to adapt to the stupidest guy in the network. But with fulcrum codes, you can know just everybody is coding as good as he can. Good. This was the storyline for network coding, and sorry that I don't have this yet for quantum networks. The reason is that this was the something about the last 2 decades what we did there, right? And with quantum communication networks, we are just starting to understand that we are on the upper part now, talking about fundamental things that can happen, but we are really interested also to the lower part now, to really make it happen, to understand where are the boundaries and what we can do to inspire the research to do it again. So let me just summarize this. I hope that I did not favor one of them. I think theory and implementation both are important, right? And I also think that the interplay is essential for the research. Otherwise, you are just doing green grass research where nobody really understands why are you doing that, right? The implementation has also something you can easily talk to the industry there, and you see what they are leeching on, right? It should not lead your research, but it it can help to get financing your research. That implementation brings also novel research questions. I hope that I could enlighten this at the moment. And it's also important for our students, for example, that they are able to program, right? A lot of people are very good on paper, but then if they have to program something, most of them fail there. I don't know where we do something wrong in our curriculum, but let's think about that. And then there's something what I really like. I like to see it work. So if you tell me on paper it might work, then I will tell you I would like to see it. And one story here from network coding, when you use network coding theory and you use the network codes for storage, right? I just talked here about transport. But if you use it for storage, it's so interesting that the implementation and the research is one-to-one. There's no glitch whatsoever. But if you take theory and, for example, wireless mesh networks, and you take your theory and you implement it, nothing works, right? Excuse me, but what I tell my students always is wireless mesh is a bitch. You cannot get the results that are on paper. There's so many things that you have to understand, how packets are queued, what is the queuing delay, what are the queues doing with the packets, right? And once you're in the queue, you cannot take it out to recode something and so on. It's a nightmare. So there's some levels that are easy to implement, and the feedback is not so big. And then sometimes it's very hard, but then the feedback on research is bigger. So the only thing I would like to conclude with is to motivate maybe everybody to work with us or work alone on this with the theory that matters on quantum communication networks. Thank you very much.
Okay, thanks for your talk, Frank. Maybe as usual, I start with these two questions we have. So the first one is, what do you think will be the first use case for entanglement-assisted communication networks?
I think that the implementation depends heavily on where we are really seeing a need in the implementation fields, right? And it depends what the individual people are doing. From our perspective, we think that it can help us a lot in using the shared randomness for network coding, compressed sensing, whatsoever. But it will also help us for low latency communication. Because I did not talk about this today, but I think Ricardo will do it later on, maybe better than I can do it, to understand that if you want to have simple operations, also based on randomness, on the physical layer, maybe it's good to do this with quantum communication and not on a virtualized world, how we are doing it today. Nowadays, what we're doing is we take the packet, we bring it up to 4th floor, we do operation there in the softwareized world, and this takes so much time. And for simple operations, we might can do this also on the nodes directly on the file layer, and that would help us for latency.